Section 12.3, Semiconductors. So semiconductors, there's two classes of semiconductors. There's semiconductors that are made up of only one element, elemental semiconductors, and then there are compound semiconductors, which are usually two or more atoms put together in a compound. And we'll look at the structure. The structure has a lot to do with which two elements can go together to be a semiconductor. But the semiconductors that are elements can be silicon. That's the main one. And it's the cheapest one. It's made out of sand, essentially. You can have germanium, which is right there in group 4 along with that. You can also have carbon. Now, not the diamond shape structure of carbon, but normal carbon. And you can also have gray tin. And these, if you'll recognize that all of these are in group 4, that means they essentially have 4 arms. And they, as 4 arms, they can hold, remember, they're not in 2 dimensions, it's in 3 dimensions. So they're in tetrahedrals. And as a tetrahedral shape, they're rigid and they are in a 3-dimensional pattern. So forward, up, and it's like tetrahedral is a triangle, 4-sided triangular prism, what it is. Okay, so a semiconductor is, since it has these 4 valence electrons, there's one single electron on each of these arms. It yields a structure that has an energy gap that separates totally filled and empty bands. And we've already discussed these bands. Here's a picture. The valence band is completely filled with electrons. Okay, the conduction band is empty, but any electrons that would flow in electricity has to be free. They have to be free to move, and so they have to be in this conduction band. In order for those electrons to be free enough to move and not bound to the nucleus, energy has to be provided. And that energy is this gap, the gap between the VB, the valence band, and the conduction band above it. And the semiconductors have a valence gap of about 50 to 300 kilojoules per mole. And you could rate that in electrovolts also. I think there's about 100 kilojoules per mole in an electrovolt. So you could do the connection there. So a semiconductor, many times, for instance, a microchip on a scratch, you scratch that microchip and it can conduct electricity, and then the other places not. It's pretty interesting. So here are the 3: carbon, silicon, germanium, that at room temperature can be. And then you can have inorganic semiconductors that have an average of 4 valence electrons. So for instance, you take one from group 3, like gallium. You have one from group 5, like arsenic. So if you have gallium arsenide, it would average to a group similar to silicon, so that could be an inorganic semiconductor. So you can even do group 2 with group 6. They can work as semiconductors also. Now, doping. Doping is a little bit weird. Let's imagine that I have silicon, okay, and it has, at room temperature, some electrons are in the conducting band, okay. I can tweak it just a little bit by adding atoms different than silicon to that silicon. So if I can just put a few silicons there, or a few other atoms with that silicon, I can tweak the conductivity. For instance, let's say that I put something from group 5. Okay, let's say I put arsenic, 1 atom of arsenic. Well, arsenic is in group 5. It has 5 valence electrons. Silicon is holding hands with silicon, and that only needs 4. So arsenic has 1 more available electron that can be used, since it's not occupied other places, it can be used to conduct electricity. So if I could sprinkle, or it's called doping, if I dope the small amounts of impurities. So let's say the impurities are very specific. It's not just dirt. It would be specific atoms that I'm introducing that have a higher valence number. Then those extra electron places can actually increase the amount of electrons in the conducting band. You can also dope with lesser. Now, by the way, to dope with higher, like group 5, would be the N-type. That's called N-type doping. And then the P-type is a little bit weirder. You are putting something from maybe group 3 in, which means it's holding hands with 3 things instead of 4. That leaves a leftover silicons hanging out, and essentially where those electrons should have been, they're not there. So it's thought of as almost like positives. And since those positives are free to move around, as the electrons can go from one empty space to another, it's like that hole, that positive hole, that's why it's called P-type, that positive hole is moving around, and so essentially it's like electricity. Semiconductors, you can make electricity flow through them in all kinds of different ways, especially if you can combine types of semiconductors that have been doped in an N-type of property, where you're adding something with a higher number of connections, say group 5, or add that N-type to a P-type, like when you have fewer bonds. So electronic silicon is perfect because it's cheap, it's made out of sand, it's also totally a conductor of electricity at room temperature, exactly when you would want it to be. Okay, so there are other applications too. By using these types of semiconductors together, you can make electricity flow. So this is an example of solar panels, so non-crystalline silicon panels which convert visible light into electrical energy. So as a light shines on one type of semiconductor, it will force electrons to flow towards a second type, and then that will allow you to connect it to your calculator or to your water heater or whatever you would want. Another really useful one is liquid crystals. And so liquid crystals have been around. You've been able to buy solar-powered calculators since the 80s. So they don't directly go from the solid state to the liquid state. They go to an intermediate state of liquid, and those are conducting of electricity. So you can turn electric circuits on and make the shape of these crystals bend towards more of a liquid, more of a solid, and then they can interchange. They can go back and forth. You can make them solid when you want them to be, and then when you don't want them to be, they go back into the liquid state. So like the numbers on a calculator, that's all liquid crystals. A lot of liquid crystals on laptop screens, or at least they used to have liquid crystals for laptop screens for that reason. Okay, so since this is a liquid, but it's a crystal, they do have order, and when you put electricity through them, they can either be transparent or opaque as you would want them to be. So you can make them dark or light just by adding a current, which is pretty cool. Okay, so the molecules are only ordered along one axis. Okay, that's called nematic liquid crystals. And then in schematic liquid crystals, they're ordered along 2 dimensions. Okay, so that means they have a different shape depending upon the conductivity. So in a cholesterol liquid crystals, they're stacked up to where you have layers of these, and depending upon the current that's flowing, they can either look clear or look dark, depending upon the current that you put them to. You can also change temperatures. So these are films that would indicate heat. You can I've got one that you can put in the microwave, and the microwave can be seen by it, and you can actually measure the wavelength of a microwave oven, which is pretty cool. And the last thing today is light emitting diodes. If you can make a junction between the two types of semiconductors, okay, you can cause light to be emitted as electrons are trying to get into the empty spaces of the p-type from the n-type. As long as you form a junction between them, they will emit light. And electricity can only go in one direction. It doesn't go in both directions. So it's a lot of times these diodes can be unidirectional and be used to test whether something is actually working correctly, one of your circuits are working